Good morning. My name is Enrica Chiadroni, and I'm associate professor at Sapienza University in Rome. I'm an accelerator physicist working on high brightness photoinjectors for interdisciplinary applications, in particular novel radiation sources and advanced acceleration technique. I'm deeply involved in the plasma-based experiments which are ongoing at Frascati, at Laboratori Nazionali di Frascati of the INFN, where also the EuPRAXIA at Spark Lab project is ongoing. In EuPRAXIA, I'm co-leading the work package on applications concerning the development of applications, the study of different beam lines, and also delivery systems for users, and in particular systems and methods for delivery beams and or radiation to users. The main point is try to preserve, and the aim is to preserve the quality of the beams and the radiation we produce with our facility, in our facility. My involvement in the EuPRAXIA project started with the EuPRAXIA design study when I was in charge of the RF radio frequency photoinjector, and starting with that experience, I then got the leading of the working area concerning injector in the EuPRAXIA at Spark Lab project, which is the site, the experimental site dedicated to particle-driven plasma wave field acceleration. Plasma accelerators, as any other accelerator, so depending on the energy, on the final energy of the beam, and depending on the characteristics, can find applications in several fields, fields of science, spanning from radiation sources generation to high energy physics. However, in my opinion, applications of plasma-based accelerators can be also found internally, in the sense that all of us involved in this project can be considered as users of the EuPRAXIA machine, of the LINAC or the lasers or the plasma modules, in the sense that also the technology development which is behind the plasma accelerators can pave the way to several other applications, and maybe unpredictable now. So plasma-based accelerators can be used in order to provide very high with radiation with a very high challenge or novel techniques, which are always worth to study. But the plasma accelerator also the technology behind this kind of machines, so plasma accelerators, can be an application as well. So we can probably know only in the future what are all the scenario of plasma activity. Okay, concerning the main challenges in the applications area, I think that the definition of a bunch of target user experiments can be an issue, because we should define a kind of bunch of parameters in order to perform different kind of experiments dedicated and focused in different stages of the project. So starting from the beginning up to when the overall machine and the overall facility will be at regime. So this, of course, should be done based on the achievable parameters and finally on the achieved parameter. Also, the proper design of the beam lines can be considered as an additional hot topic, since the beam lines should guarantee the transport of a high quality beams, high quality radiation in order to deliver to deliver to the user's end station the best radiation pulse they need. In the case of users radiation for user applications, user for radiation applications. But in case of different applications, which might be, for instance, the test of a novel diagnostics for which the beam directly accelerated in the plasma can be used. Also, the way we design these beam lines has an impact on the final goal. So the design of the delivery systems is not trivial, because the beam which are coming out from the plasma accelerators are not so far as the conventional RF accelerator. So they also have some particular characteristics which might be considered, in the sense that in order to get the very in order to not introduce artifacts in the beam quality. As first, I think that compactness is the main, let's say, the main difference and the main quality with respect to conventional radio frequency accelerators, because compactness is not intended only considered to plasma modules, to plasma accelerating modules. So because is not only the footprint of the plasma accelerating module, which is reduced because of the high gradients which can be achieved in the plasma, but also ancillary components can be reduced. And when I say ancillary components, I'm thinking to, for instance, plasma lenses in order to focus and let's say guide and transport the electron beam. Also, there is also some R&D on plasma dipoles, which can be used to bend the beams in a very short distance. We can also think there are several ideas to use plasmas also as diagnostics. Actually, there was an idea of a few years ago of using plasma for as a deflecting cavity, so in order to measure the longitudinal beam size. So there is a lot of R&D which is ongoing, not only on the plasma module for acceleration, but also for other components of a real accelerator. So if we place all together, we really can think to squeeze the size of an accelerator of many orders of magnitudes. So compactness is, in my opinion, is the main strength of this kind of accelerator. Of course, the possibility, and this is of course given by the fact that it is possible to reach very large accelerating gradient.